Hello and welcome back. In this video we'll cover a possible solution to moving from a very simple fully connected neural network in image classification to a convolutional neural network. So this is the same notebook we had before, we just replace the neural network now. So let me skip over. We have accessed the data, we have defined the data loaders, and now we move on to the network definition. Before we had used this neural network, we have used linear layers with the input one, the output 1 to 10 classes, and simple linear layer between, and defined the forward pass where the data is flattened from the 2D structure into essentially a 1D array, and then we move on through the network input layer, activation function, hidden layer, activation function, output layer, and return the object. Now we use a more complex model and build a still fairly simple but a convolutional neural network. So in our initialization function, we need to define now the convolution operators we want to use. And because we use on images, we use a 2D convolution. And then we need to define channels that we want to use, the output channel, the input channel, and the important parameters of the convolution, the kernel size, and the stride. So we use 3, 3, and 1 for these ones. And we need to define 2 ones because we want to use 2 convolution layers. One of the more tricky things is to calculate the output of the convolution of the second layer. And this you can do with this formula. It's best to sort of keep it handy and remember it. So this gives us an idea of how we can come up with a number that we need to put here, for example, right, and after the max pool as well. We also need a few linear layers. So we need the output, these are the 10 classes, and we need some regularization for the program. And now we pass the data through the network. That means we need to define the forward pass. We pass the image itself into convolutional neural network layer. So remember up here, we used flatten and then use it in a linear layer. Here we don't use flatten but pass it to the convolutional layer, use the activation function, then use the second convolutional layer and the activation function. So essentially here, these are the learnable filters that we want the network to learn. So here the network learns to build sort of itself some features out of the data itself. Now we need to do the max pool operation and flatten this, because at the end we still need to do the classification, right? We need to distinguish between the 10 digits, and before we've just given it as an array, but here we want the network to learn what the image is about, and these convolutional networks will learn the features from the images. But in order to make use of this, it's like an automatic feature engineering. If you want to make use of these features the network has learned from the data, we need to put it into a fully connected layer, into the FC2, the fully connected layer 2. This is, if we scroll back up again, this is the one that has the 10 output classes. So this defines our new neural network, and the rest is the same. So we define our loss function, the optimizer, the training loop just as before, right? We loop over the data in batches, put the model into train, make a prediction of the current state, calculate the loss function, do the backward part, tell the optimizer to move and wiggle around the network weights in the right direction, take the accuracy in the test part on the test data, and then loop for 5 epochs over the data. If we do this, we can see that not only does the loss function continue to improve, but also the accuracy improves each time. So we now reach an accuracy of 99%, which is already fairly good. But remember that the best networks here get a lot better. So we would have to improve our network if we were to beat this.